Question 16 is strange because of the constraints put on possible solution paths due to the lack of reference information available. It's perhaps the most likely question that a tester will pursue dead-end solution options, even though they would otherwise be reasonable ways to solve it. Initial critical thought solution elements. 1. What are you solving for? GPM flow for one branch in a parallel piping system. 2. What is the fundamental process? Balancing flow based on fundamental laws for parallel systems. 3. What are the first considerations to find the solution in connection to the fundamental process? Determining what is necessary information for calculating friction head and if it's available. 4. Are there key assumptions? Ideal adiabatic steady flow conditions with no fluid compression. This video is brought to you by ExOverZero, which offers the best HVAC PE steady material possible. Want to pass the test? Buy the books. Use the link below to purchase. To solve a problem like this in the real world, it would be natural to open up a reference like Cameron hydraulic data to the table on page 3-14. There you would find data on friction, velocity, and head loss for water in 1-inch Schedule 40 steel pipes. But you won't have Cameron in the test. You'll only have the Ncees Mechanical Reference Handbook, and there are no tables like that in there. Here's an important place to stop and consider. How long did you spend, or would you have spent, trying to find helpful table data in the reference handbook? You only have an average of 6 minutes to solve each of the questions on the PE. Chances are, if you've already attempted this question, you spent more than 6 minutes just trying to find something helpful out of the handbook. Speaking of things that are not in the reference handbook, the best place to start the solution path is in the fundamental laws for parallel piping systems, a topic that's also not covered in the handbook. The HVAC PE is considered under the broader discipline of mechanics, and a fundamental concept that every engineer of mechanics needs to know is the difference between operating principles of parallel systems and series systems. Expect your knowledge of series versus parallel to be tested in the PE. These are multi-pipe systems. Here are pipes in series. Here are pipes in parallel. There are two sets of opposing laws that govern the flow of liquid through them. For series, 1, the volumetric flow rate is the same in all individual pipes, and 2, total head loss is the sum of individual pipe head losses. Now the opposites. For parallel, 1, total volumetric flow rate is the sum of all individual pipe volumetric flow rates, and 2, the head loss is the same in all individual pipes. These laws are demonstrated in pump performance curves. Look up section 3.7.4 in the Ncees Mechanical Reference Handbook to see these curves, pages 234 in version 1.1. Notice how, for parallel operation, the curves have the same head, but the flow changes. Also, notice, for series operation, the curves have the same flow, but the head changes. From electrical circuits to pipe systems to pump performance, you must understand series versus parallel if you are to understand mechanics. This question is for a parallel piping system. The total 20 GPM system flow rate will be made up from the sum of two different flow rates. The solution is for one branch's flow rate. The two branches will have the same head loss. Use the matching head loss as a balancing principle to derive the different flow rates. Because there's lots of missing data, balance the two branches using a form of equality cancellation for what's missing. You don't outright determine the head, but you know it's the same for both branches. How is head calculated in piping systems? First, recognize what kind of head it is. No altitude information is given, and the system is closed off from the atmosphere, so it isn't altitude head or atmospheric pressure head. The question does give information about elbows and valves. Both contribute to friction head loss. So solve for friction head loss for water flowing in pipes. In the NCEES Mechanical Reference Handbook, look up section 3.4.2.1 for the Darcy-Weisbach equation. Expect to be tested on this equation on exam day. No friction factor is given, but you know they're the same, so use equality cancellation. Pipe diameter and gravity are the same as well, so use equality cancellation. All that's left is length of pipe and velocity of flow. There are two different lengths. Branch A is simply the pipe length. Branch B is the sum of pipe length, valve equivalent length, and elbow equivalent length. If the head is equal and the length is different, then the velocity must also be different to counteract the different length and make everything equal out. For piping systems, velocity and volumetric flow are closely linked. Volumetric flow can be defined as velocity times the pipe cross-section area. So, if you know the pipe diameter and velocity, you essentially know the volumetric flow. Further, if the two branches of the system have the same pipe diameter, by equality cancellation, this ratio for balancing the two is the same for velocity or volumetric flow. Set this equation up. Divide. Square root. So the ratio for balancing is roughly 1.37. That means branch A's flow equals 137% of branch B's flow. Using simple substitution, 20 GPM total equals 1.37 times branch B plus branch B. Branch B equals 8.44 GPM. Option B. To get good at questions like this, you should already have a good idea of what's in the NCEES Mechanical Reference Handbook, and maybe more importantly, what's not in it. Get to know it really well, the only way possible, by practicing lookups in it. To do this, ExOverZero has a one-of-a-kind drill book for the NCEES Mechanical Reference Handbook. Use the link below to purchase.